Welcome to a lesson comparing exponential functions in the form f of x equals a times b raised to the power of x and f of x equals a times e raised to the power of kx. When we have an exponential function in the form f of x equals a times b raised to the power of x, a is the initial or starting amount, the base b is equal to 1 plus r, where r equals the growth rate per unit of time as a decimal. So if the base b is greater than 1, then r would be positive or greater than 0. So we have exponential growth, and we have an exponential growth rate per unit of time equal to r. Now, if the base b is between 0 and 1, then r would be less than 0 or negative. So we have exponential decay, and we have a decay rate per unit of time equal to the absolute value of r. So the important thing to recognize here is that the growth or decay rate is per unit of time, meaning it could be per year, per quarter, per month, and so on. Now comparing this to f of x equals a times e raised to the power of kx, a is still the initial or starting amount, but here if k is positive or greater than 0, we have exponential growth, but we have a continuous growth rate of k. And if k is less than 0 or negative, we have exponential decay, with a continuous decay rate of the absolute value of k. So here we can inspect the function to determine a continuous growth or decay rate. And in this form here, we can analyze the base b to determine r, which will tell us the growth or decay rate per unit of time. Let's look at an example. Here we're given a function that models the number of cell phones in the US since the year 2000, where n of t is the millions of cell phones, and t is the number of years since 2000. We're asked to determine the annual growth rate and the continuous growth rate. So the first thing we should recognize here is that the given function n of t is in the form a times b raised to the power of t, and therefore by analyzing the base b, which equals 1 plus r, we can determine the annual growth rate. We'll have to perform some calculations to determine the continuous growth rate, which would be the value of k in this form. So because b is equal to 1 plus r, we can also say that r is equal to b minus 1. And here the base is equal to 1.33, so we can say r is equal to 1.133 minus 1, which equals 0.133. So the annual growth rate is equal to 13.3%. Let's go ahead and write this down. The annual growth rate is 13.3%. Now we need to find the continuous growth rate. So to do this, our goal here is to really write an exponential function in this form that's equal to an exponential function in this form. In order for these two functions to be equal to each other, notice how b to the x would have to be equal to e raised to the power of kx. So if we have b to the x equals e to the power of kx, we can also write e to the kx as e to the k raised to the power of x. Notice in this form, we should be able to recognize that that means the base b must be equal to e to the k. So if b is equal to e to the k, and we know b is equal to 1.133, in order to find k, the continuous growth rate, we need to solve the equation 1.133 equals e to the k. So to solve this exponential equation, we can write the exponential equation as a log equation using the definition of a logarithm shown here, where y equals e to the x is equivalent to x equals natural log y. So write this as a log equation. Because we have base e, we'll have natural log. A logarithm is an exponent, so we'll have the natural log equal to k, and e to the k is equal to 1.133, so we have k equals natural log 1.133. And now we can go to the calculator to get an approximation for k. We'd have natural log 1.133, which to 4 decimal places would be approximately 0.1249, which means as a percentage, this would be 12.49%. So now we know the continuous growth rate is 12.49%. Now for the second part of this question, we're asked to write the given exponential function in the form n of t equals a times e raised to the power of kt. Remember, we just found that k is approximately 0.1249, This is all we need in order to write an equivalent exponential equation in this form here. We would have n of t equals a, which is the same initial value as the first exponential equation, so 110 times e raised to the power of k, which is 0.1249 times t. So here's the equivalent exponential function written with base e. Now let's take a look at a second example. You buy a new computer for $1,500. The value of the computer in dollars is given by the function v of t, where t is a number of years after the purchase. We're asked to determine the continuous depreciation rate and the annual depreciation rate, and then rewrite the given exponential function in the form v of t equals a times b raised to the power of t. So the first thing to recognize here is that the given exponential function is in the form of a times e raised to the power of kt. So by determining the value of k, we can determine the continuous depreciation rate. So notice here, k is equal to negative 0.325. So if we know that k is equal to negative 0.325, as a percentage, k would be equal to negative 32.5%. It's negative because the value is decreasing at this continuous percentage rate per year, and therefore we know that the continuous depreciation rate would be 32.5%. Because we're saying depreciation, we do not include the negative. So the continuous depreciation rate is 32.5%. And now to determine the annual depreciation rate, we need to determine the value of r when we have the exponential function in this form here. To find the value of r, we'll use the same equation here to find b. Once we find b, we can determine r. So using the equation b must equal e raised to the power of k, well, we know the value of k is negative 0.325, so we have b equals e raised to the power of negative 0.325. And now we just need to go to the calculator to approximate e raised to this power. So we'll press second natural log, which brings up e raised to the power. So we just enter negative 0.325, enter, which gives us approximately 0.7225. So b is approximately 0.7225. Because we know b equals 1 plus r, we know r equals b minus 1. So we have r equals 0.7225 minus 1, which is equal to negative 0.2775. So we have r equals, as a percentage, negative 27.75%. So because this is negative, we know we have exponential decay, and it's decaying at an annual rate of 27.75%, which means the annual depreciation rate is 27.75%. Again, we don't include the sign because we're stating it is a depreciation rate. And now for the second part of this question, we're asked to rewrite the exponential function with base e in the form v of t equals a times b raised to the power of t. And we just found on the previous slide that b was equal to 0.7225. So if we know b equals 0.7225, and we know a is still going to be 1,500, we can easily write the given exponential function in this form here. We would have v of t equals 1,500 times the base 0.7225 raised to the power of t. So this would be an equivalent exponential function with base b rather than base e. I hope you found this helpful.